Today we are continuing our lesson on machines. And again, we're still talking about this idea that you're doing the same amount of work, but you're allowed to do a lesser force, so it makes your work easier. Okay, so machines make your work easier. They don't let you get away with doing less work. So when a machine changes the size of the force, the distance also has to change. Force or distance can increase, but both cannot increase on the same side of the equation. I'm going to show you what that means. So when one increases, the other has to decrease on the same side. And we showed this with some examples on the last one. So let's say the force in. Let's say you're doing a lower force in. That means you have to do that force for a bigger distance. That means on the outside, the machine is going to give you a bigger force over a smaller distance. Okay? Notice how they're opposite. Little force in gives you big force out. Little distance out is big distance in. Okay? And they have to be opposite. They have to be little big, big little. Alright? It could be big force in over a little distance will also equal little force out over big distance out. Okay. You can do it that way too. You just can't have big and big on the same side or little and little on the other side. It's just impossible. Okay. When one thing increases, the other has to decrease. Okay. So again, you can put little force in over a big distance, and you're going to get lots of force out over a small distance. Or you can put a lot of force in over a little distance and get a little force out over a big distance. And we're going to do lots of examples with this. So let's start with this picture. A nutcracker. So imagine you have a walnut, and if you just put that between your fingers and tried to squeeze, you would never be able to crack it. But if you use a simple machine as a nutcracker, it's easy. Okay? The inside here, okay, you have a big distance in. Okay? So if you have a big distance, okay, big distance means the force can be small. Okay? Big distance means small force, and that's going to equal, okay, here, look at that little distance. Only a little distance right there that it's moving. So you're going to get, if you have a little distance that you're getting out, you are going to get a big force out. Okay? So it helped you. It made your job easier. You could apply a little force over a big distance and get a lot of force out over a small distance. Okay? Hammer is kind of the opposite way. Okay? For a hammer, the distance you swing, very small. Okay? So small distance means that you have to apply lots of force. Okay, it's the inside. But getting out, that hammer swings a long way. Okay, you get out a big distance, which means, unfortunately, you get out only a little bit of force. Okay, big distance, little force. Okay, usually this isn't the type of machine you're looking for, but that's all we have with a hammer, unless you're using a pneumatic one. Okay, and this is also why your hand feels so tired. You know, after you pound in 10 nails, 20 nails, your hand gets really, really tired because you have to put in a lot of force. The benefit is you're getting that distance out, and you want that distance out so you can get momentum to drive the nail in. The single fixed pulley here, the distance you pull down, okay, is equal to the distance the object goes up. Well, if the distance is equal, that means the force has to be equal. So what's the benefit? The benefit is it changes the direction. Okay, so that's the key, it's changing the direction for that one. The paint can here with the screwdriver, we already showed this one on the last lesson. You had a big distance. Okay, so your input was a big distance, which means you got to do a little force. But on the outside, you got a large force and a small distance. Okay? So you get to input a little force over a big distance, but out you get big force over a little distance. A way to kind of figure out how much advantage you're getting to this is called mechanical advantage. Mechanical advantage is the number of times that a machine multiplies the force. It's going to compare input force with output force. Okay, the key is force, not work, force. Okay, you're comparing input force with output force. I like to think of it as how many times easier does the machine make my work? Okay, did it make it 5 times easier, or 6 times easier, 10 times easier? How much easier did it make it? The formula is really simple. Mechanical advantage is output force divided by input force. That's it. So you push a piano that weighs 600 newtons up a ramp with only 60 newtons of force. What's the mechanical advantage? Okay, mechanical advantage equals force out divided by force in. Okay? The force out, remember, is the object. The piano weighed 600 newtons, so that's my force out. So 600 newtons force out divided by my force in. That's what I did. I did 60 newtons in. Okay? So 600 divided by 60 is 10. What's my unit label? I had a newtons over newtons. Don't those cancel out? Yes. No unit label. 10. Okay, that's my answer. Because remember, it's how many times the machine multiplies the force. It multiplied the force 10 times. It made it 10 times easier. Okay? Means, of course, my distance that I had to do it was 10 times longer. Okay, so my ramp was really long ramp. It was, my ramp, if this is the ground, my ramp looks something like this. It was an incredibly long ramp. But hey, it made my job 10 times easier. So I'll take pushing it 10 times longer. A machine with mechanical advantage greater than 1 helps moving or lifting objects because the output force is greater than the input force. Okay, so usually we're looking for this mechanical advantage greater than 1. Okay, the last example, mechanical advantage was 10. Okay, it made it 10 times easier. So we're looking for mechanical advantage greater than 1. Sometimes, though, you're going to have a mechanical advantage less than 1. When you do, it's going to reduce the output force, but it increases the distance. And again, the hammer was a good idea of this. All right, you were getting that big distance out to gain momentum to put the nail in. It required a lot of force, though. A lacrosse stick is another good example of this. Okay, your hands are down here somewhere. Okay, so you swing a little distance, but you get a ton of distance out. Okay, that's what you want because your ball doesn't weigh much. Okay, the little lacrosse ball, it doesn't weigh much, so you don't need to get a big force out. Okay, it doesn't weigh much, so that you get to swing it a long way and get a lot of momentum and throw it really fast. Okay, if you have a really long stick, you can throw it really fast because you're gaining lots and lots of distance. Okay, that's going to be a mechanical advantage less than 1 though, because you had to put more force in than you got out. The force out was smaller than you got. Okay. If I go back, remember we had our example here with this, and we had our work out. If you remember, we multiplied 400 times 2, and that was 800 joules. Okay. Our work in, remember, was 840 joules. Okay. My force in, okay, that 800, if you remember how we got that, was 400 times 2. Okay, and this one was 210 times 4. Okay, so what's the mechanical advantage of this? Okay, the mechanical advantage, again, is force out divided by force in. So we do that, and we had 400 divided by 210. Okay, so 400 divided by 210, and that gives us almost 2 by rounding. I guess we don't round. Significant digits, yeah, we'll round to 2. Okay, so it made my job twice as easy. Okay. Now, it may have made it twice as easy, but did it waste some energy? That's what we're looking at with mechanical efficiency. Remember, the work output of a machine can never be greater than the work input. Why? Because there's always a little bit of friction. And that friction is going to use up some of our work. Okay? The less friction there is, of course, the more efficient the machine is. We want an efficient machine because it's going to use all of our work, or most of our work. Mechanical efficiency is just the comparison of a machine's work output. Okay, notice we're doing work, not force. So work output with work input. Okay, mechanical advantage was force output and force input. Mechanical efficiency is work output and work input. So the formula is just work out divided by work in times 100. So it's going to be a percent. So if I go back to that example that I had with the wheelbarrow back here, if I want to find mechanical efficiency, okay, for this wheelbarrow, mechanical efficiency is my work out divided by work in times 100. So mechanical efficiency was 800 divided by 840 times 100, which will give me, and I'm just going to keep it with 2 digits, it's going to give me 95% efficiency. Okay, that's a pretty efficient machine. 95% is pretty good. Okay, most of my work was used. If we go back then to where we were, what are some things that we can do to make a machine more efficient? You can use ball bearings like these. Oil is one of the main ways. Lubrication. Okay, you're going to get rid of friction. You're going to make your machine more efficient. Okay, friction is what caused the inefficiency, so you want to lubricate to get rid of that friction. Let's finish with a couple examples. I used a machine that did 30 joules of work on the object, but I had to do 60 joules of work to the machine. What is mechanical efficiency? So mechanical efficiency equals 30 over 60, okay, the out over the in. That is a horrible 50%. Okay, very inefficient. You know, need to oil it or something. That's pretty bad. Okay, using a pulley, I lifted a 40 Newton object 2 meters. I had to pull down 8 meters of rope with 11 newtons of force. What is the mechanical advantage of my pulley? And then what's the mechanical efficiency? So we have to start with mechanical advantage, and I have to get my work first. So remember, work out is force out times distance out. Work in is going to be force in times distance in. Okay. Remember, the work out is what the machine's doing. It's lifting 40 newtons 2 meters. So 40 times 2 equals 80 joules. Okay, so my work out is 80 joules. Work in is what I did. I pulled 8 meters with 11 newtons of force. So 11 newtons times 8 meters gives me 88 joules. Quick check, did I do more work than the machine? Yes, 88 compared to 80, so we know I did it right. So the mechanical advantage then is the force out over force in. Okay, so 40 divided by 11. That's going to be 3.6. Okay, if I keep 2 digits, let me just keep 2 digits to make it easy. 3.6 for mechanical advantage. My mechanical efficiency is my work out divided by my work in. So that's going to be 80 over 88. I did a little bit more work times 100, and that will be 90%. Okay, so it's 90% efficient. not too bad. Maybe I need to oil my pulley a little bit to get it a little bit more efficient, but that's not too bad. Okay, we're going to do lots more examples of these in class before we finish up with simple machines.